Hello, welcome back at Golden Ratio. This is Professor Lou Feijs of Eindhoven University of Technology, and today I will be continuing my explanation of how mathematics will be useful in your creative projects. Today's topics are the classic curves. In particular, I will zoom in to ellipses. These are the resources of today's lecture. So you need processing, which you can download for free, and on GitHub you will find the PowerPoint slide and also two of the example programs which I prepared for this lecture. There is also an external link, the Math World, maintained by Wolfram, which has excellent theoretical explanations of the things I will explain today. Let's start with some inspiration. Today's topic are ellipses, and here you see an artwork by Alexander Calder. Probably you know the guy who invented the mobile. He was fascinated by ellipses, and here you see one of his artworks. As early as 1915, Piet Mondriaan, the famous Dutch modernist painter, created this abstract artwork called Pier and Ocean. It takes some imagination to still see the pier, but you can see the waves, and the gestalt of all of this is an ellipse. The ellipse is actually one from a family of curves which I call classic curves. You have the so-called conic sections like parabolas, hyperbolas, circles, and you can treat them all in the same way using the same approach as I today will go in depth with the ellipses. Here you see a more recent artwork. If you happen to be in Bilbao, in Basque Country, in the Guggenheim Museum, you can see these huge installations which are called torqued ellipses. It's a three-dimensional thing. The floor line of this object is an ellipse. The top is also an ellipse, but the two ellipses have the longitudinal axis not aligned, which makes it a very interesting object. Today I will be talking about ellipses, where you encounter them in nature, a little bit of mathematics about it, and two examples in processing, one which illustrates the generate and test approach, and the other which is about thread art design. Ellipses in nature. First, take a few seconds. I ask you, where do you think ellipses occur in nature? Do you have an example? Probably you know, but give it a try. Well, here are my propositions. They're not the only ones, but these are examples where ellipses occur in nature. So if you have circles in reality, coffee cups, vases, and you have to make a painting of that, you will have, by the laws of perspective, to draw circles. The orbits of the planets and the moons, you knew that. And also theater designs where you encounter special acoustic effects. Here, for example, is a painting by a Dutch medieval or Renaissance painter, and here you see the vases and the glasses. But in the oblique view, drawing the perspective, the painter has to draw the ellipses, which is how you see those objects. So here you see one, for example, here you see the other one. If you decompose this work, you will find a dozen of them. The other situation where you encounter ellipses in nature is the orbits of planets and moons. You know, the Earth is going around the Sun, but the Sun is not in the center of the figure we make. The Sun is in one of the focus points of an ellipse. And you have the same here. This book comes from, this picture comes from a book on, how you call that, astronomical life. It's about satellites, and also the artificial satellites, the GPS satellites, for example. They also run in the same type of ellipses, the Earth being in one of the orbits. This has been discovered already by Kepler. Here you see a picture of Kepler, you know, the motion laws of Kepler. You also encounter them, and then it's not really nature. Actually, these satellites are not really nature. Like here, this is in the city of Trier, not too far away from Eindhoven in Germany, and there is an old Roman theater, almost 2,000 years old. I've been there, and there are special positions in the theater. You see the two little figures there. If one figure there whispers something, the other will very clearly hear it, because the sound goes in all directions, but it will bounce off the wall. And that's also why these special points are called focus point. The sound wave will come together at a single point, the other focus point. And this is something which is working in acoustics. You know, parabolas, they have the same properties. Satellite discs also have this, but then one of the focus is on infinity, so that's slightly different, and you have one focus point. That's where all the heat or all the radio waves assemble. So these are the ellipses in nature. Next, I'd like to explain you the mathematics of ellipses, and there are two approaches. One is looking to the geometric properties, where we see the focus points, and where each point at the ellipse has a constant sum of distances to those two focus points. We can also do it with equations, and then there is the standard equation, which is good for algebra, and the parametric equation, which is good for developing programs. The mathematics of the ellipses was already quite well known by the ancient Greeks, Euclid, for example. So I will make a summary of that now. If we have an ellipse like this, then it's characterized by two focus points, two foci, say this one and that one. Usually we call them like F1 and F2 for focus. And you also have the dimensions of the ellipse. For example, the long axis is usually called 2a. So A is like a radius, except for the fact that the radius is not constant. You have to work with two radiuses, because we also have the short axis, which we say to be 2b. And then the distance between those focus points, that's 2c. So these are the numbers which characterize the ellipse. The interesting property is that if you travel from the focus point to a point at the edge of the ellipse and travel back, that the sum of those two distances is constant. So if this is r1 and this equals r2, then the basic idea of the ellipse is that r1 plus r2 is a constant. We also know this constant, by the way, because we can put the r1 and the r2 both going in this direction. So if the r2 is this and the r1 is that, we can see how it works out. In that case, this one, the shortest of them, say r2, that one equals a minus c, and the other one, the longer one, going from here to there, that's a plus c. If we add those up, we see how it works with this constant distance, namely r1 plus r2 equals 2a. In other words, the 2a, which forms the long axis of the ellipse, is also this constant from the equations, which says that r1 plus r2 is constant. So here we have established a relation between this idea of constant sum of radiuses and this number a. We can also establish a further relation between the a and the b and the c. So let's draw the same ellipse here again. with its two focus points. Now suppose that we have a look at this point which is in a kind of symmetric position. Then we can again see the R1 and the R2. For example, here we have the R1 and here we have the R2. They are actually the same in this case because of the symmetry. And here we have this little distance, which is C. We have this vertical distance, which is B. And you see that this is an opportunity for applying Pythagoras' law, namely, this is the hypotenuse. It's called R, which is the same R1 and R2. Let's say this is R2. Now we see here a rectangular triangle, and Pythagoras' law says that b squared plus c squared equals R2 squared, but I know something else about this R2, namely R1 and R2 together are 2a. They are the same. So as a matter of fact, this R2 happens to be a. So now we see b squared plus c squared equals a squared. This is very convenient because these relationships are interdependent. If we do these geometric properties and this sum of length, it's nice to know the positions of the focus points. That's why we need C. If we generate the ellipse in a computer program, we usually start from the B and the A. We can also use this to check whether a point is inside the ellipse or not. So if you have this ellipse here, say, and now I want to consider a certain point and test whether it's inside the ellipse. Let's say this point here. Well, you can clearly see that it's in the ellipse, but can we do that in a formal way? Well, then we have those two radiuses here, R1 and R2. Normally, if you are at the edge, R1 and R2 together should be 2a. Here we have that the point, say this is the point x, y. If we think in coordinates, then the point x, y is in the ellipse. If, precisely if R1 plus R2 is less than 2a. And how would I calculate that R1 and that R2? Well, for example, if you work in processing, you have this distance function which can calculate the distance between one point and the other. So the distance from this point x, y to the x and the y of the focus point, say if the origin is here, and this would be the point minus c 0. So now we have this one distance. In the same way we can do the other distance. And that sum must be less than 2a. Now we have a very practical test for finding out whether a point is inside the ellipse or not. Of course, this is very useful in generate and test approach. The next topic, this was like the geometry of the ellipse. The next topic is about the equations of the ellipse. So this was the ellipse from a geometric point of view. Now I like to discuss the same ellipse by means of equations. If you look up the equations of an ellipse, the typical thing you will find is that the books tell you that x squared divided by a squared plus y squared divided by b squared equals 1. This is working in a Cartesian approach, so we have coordinate x and y. We have the numbers a and b, which characterize the ellipse. And we work in a coordinate system like this. So suppose we have a vertical axis, which we label y, and a horizontal axis, which we label x. Then the ellipse is like this. Each point has a x, y coordinates. And again, we have the A and the B. So here we have the equation. But in practice, this equation is not very useful. It's nice if you like algebra, but if you like to make generative programs for all kind of aesthetical purposes, then there is another equation which is much more convenient, namely the parametric equation. These are better, and the idea is that you start from an angle, say theta, and that can be used in an algorithm to be changed, incremented in small steps, delta, theta, for example. So these equations are slightly different. The equation says x equals a times cosine of theta and y equals b times sine of theta. You may have a déjà vu on these equations because they're very similar to those of the circle. In a circle we would not have a and b here, we would have the radius. A circle is an ellipse with the long and the short axis being the same. So you can also say an ellipse is essentially a circle, but we have messed around a little bit with the factors. We have done a kind of horizontal stretching of in the x direction, the a perhaps being larger than the original radius, and we have done a kind of compression in the vertical direction, the b being less than the original radius. Of course, these two equations are equivalent. I will show that to you. For example, if we try to calculate x squared divided by a squared, we get a squared cosine squared theta. We can divide that by a squared. So now we have this one. We can also calculate y squared divided by b squared, so then we get b squared sine theta squared divided by b squared. Of course, you see that the a squares cancel out, so here we have cosine squared, here we have sine squared. If we add them up, we get cosine squared plus sine squared theta equals 1. And this is a well-known trigonometric property. The sum of squares of cosine and sine equals 1. Essentially, it's Pythagoras' law in a little triangle where you take the hypotenuse to be 1. Then this just equals the sine, this just equals the cosine, and together, if you square them, they are 1. What this shows is that indeed, if we calculate starting from the parametric equation, by some manipulation we have gotten rid of the theta and we have recovered the general equation. So you can feel reliable that this works correctly. The parametric equation is nice for producing the ellipse. For example, if you want to create the ellipse in a stepwise manner, You have the coordinate grid. You start with theta equals 0, then you have a point, then you add a little bit, a small step, d theta, you get a new point, you get a new point, you get a new point, and in this way you can make the ellipse approximated in any number of points you want. This is also what we will do in the program, the second program, where we approximate the ellipse. Well, this is all you need to know of the mathematics of this classic curve. Parabolas are and hyperbolas go precisely in the same way. Now it's time for some aesthetic programs. Okay, now we had a look at the mathematics of the ellipse, and we are going to deploy that mathematics in two examples. The first example is of the generate and test approach, and here we will draw simple basic figures only if they are in the ellipse, and that's where the generate and test, why it's called generate and test. We just throw them randomly all over the screen and we keep those which are in the ellipse, and that's why we have this inequality. Sum of distances should be less than 2a, as I explained on the blackboard. That's the core formula there. The other is the thread art design. There we will use the parametric equation. Here you see the first example, which is about testing whether a point x, y is inside the ellipse. The ellipse is in the center of the screen, and it has a long axis of 2a and a short axis of 2b, taken 200 and 100. And you also see that there is a relation between the a and the b and the c, which is calculated here, square root of subtracting the squares. I made a small auxiliary function of squaring, and then the radius 1 of the xy point is calculated with the distance function, the radius r2 also, and it's like having the rope from the r1 to the point which is under consideration back to the other point. If the sum of those two distances, those two pieces of ropes, is less than 2a, then the point is inside the ellipse, otherwise it is not. And here you see how we use it for making something larger. The picture is built up incrementally, so in the draw each time a little rectangle is created only if the point x, y is in the ellipse. The coordinates of the ellipse are supposed to be around 0 as the center, so here we subtract the center of the screen from that in order to have a simple equation. There is another technique which I use here, which I call Lacanian programming. I call it after a famous French psychotherapist who had a strange habit of stopping the sessions with his patients at an unexpected moment, so as to leave a kind of maximum tension for the patient to work on, which was not standard because standard sessions would run 50 minutes. We will do the same here with the program, so it generates and it generates and it generates, and at some point we see, this is enough, this is a good composition. Then we hit the mouse and the program will save the PDF. You see also here the begin PDF and the end PDF. This is very powerful. It's much better than doing screenshots, because now you will have high resolution vector graphics. If later you're famous and your artwork has to reproduce on the front of a huge building, it will still be sharp. That's a very good technique. Here you see that in action, generating small rectangles more and more, until at this point I decided this is good enough. It need not be rectangles. You also can do something else. Let's say you like my shirt, the Memphis colors and these circles. Ta-da, now we have an ellipse kind of filled by these Memphis color circles. Okay, now we move to the second example, which is thread art. So the idea is to create the ellipse, but approximate it by points, say 50 points, number n equals 50, that's the number of points, and then those will be pins around the ellipse. So there you also know how to use the parametric equation. The angle is being incremented by small steps, like rotating, each small step being 2 pi divided by 50. Now we're going to connect those points by lines, and we jump over a certain distance. In this case we will jump over j equals 13, and then we go from a pin, say I, to I plus j, so we go round in larger steps. You get the nicest effects when the least common multiple of this n and j is nothing less than the product of n and j. In other words, these numbers should be relative prime. Like 50 and 13, they have no common factor. Here is the example. And it works in 2 steps. First, calculating all the coordinates, and the coordinates are put in an array for later usage. Here you see the array, all the x values, n of them, all the y values. The landmark of the arrays are these square brackets. And then in the setup, there is a for loop which creates the ellipse. Here you see the parametric equation. The x is a times the cosine of t, and the y becomes b times the sine of t. And the t is incremented in small steps, very similar to the way one would do it for a circle. Then the point is drawn. It says point x, y, but it's also stored in the array, so each point gets its own position in the array indicated by x square brackets I and y square brackets I. So now we have those data, and then in the draw program we're going to jump through that array. We're going to do that n times. If we reach the end, well, the program is finished and we save the vector graphics. And here you see we're going to have red lines, stroke weight 2, and then the line goes from the x and the y of a certain pin to the next pin, but the next pin is not at position pin, but we add j. After a while, of course, 13, 26, 39, after a while we will be above 50, and then we jump back. So here you see this percentage sign, which is modulo arithmetic. So it goes back by subtracting 50, and in that way the numbers go round until we have had all pins. It looks like this. If we take n equals 50 and j equals 5, you see that after a number of steps we are back at the same position and we have skipped too much. If we take those numbers to be relatively prime, then there will be a single flow of lines until the whole ellipse is covered. This is the end of the programming work and the mathematics. I would like to conclude by showing a little artwork. So I had this program, I played with it, so then this can be printed, or perhaps this. So I printed several versions, and then you can take a wooden plank. We took MDF and I nicely decorated it with interfacing, and you hammer the nails on it. You use a rope, and then you can easily connect it, getting this type of artwork. We call it thread art. The hammering and the knotting of the rope is nice handwork, but the precision comes from the computer program which has been used for preparing this. So let's look back what we did in this lecture. We went in depth on the ellipses, but this is just one example of so-called conic sections. For example, the parabola, the hyperbola, you can treat them in the same way, very similar. Lissajous is also a close cousin of the ellipse. it can also be approached in the same way. For generative design, it's important to keep in mind that you need to take the parametric equation. If you go to Wolfram Math World, for example, you will find a lot of equations, but you have to look for one which is of the parametric type. Then you can do programming. The two programming programs illustrate a number of programming principles: the generate and test approach, the Lacanian ending, the idea of pre-computing coordinates and put them in an array, the jumping around using modulo arithmetic, and the technique of saving the output in vector graphics format. That's today's lecture. Next session we will continue, but we will have more sophisticated curves such as cardioids, and we will have more artistic examples. Thank you for your attention.